The prototype sat on a work table in Herstal under fluorescent lights that had burned since morning. Jean-Paul Denis and René Prédaza studied it from different angles. A compact polymer chassis with a magazine lying flat along the top like a sleeping animal. Outside, February rain drummed against the Fabrique Nationale engineering building where equipment had been designed since 1889. The NATO requirement document was precise. Create a tool capable of defeating Soviet Krypton protective gear at 150 meters, weighing less than 3 kilograms loaded, measuring under 500 millimeters in total length. The request had emerged from a quiet acknowledgement among planners. Most personnel never engaged in direct exchanges, yet they carried equipment everywhere, and those long steel tubes interfered with vehicle operations, radio work, medical duties, and the 1,000 non-active tasks that consumed 90% of service time. Denis rotated the prototype. The magazine, transparent polymer revealing brass cartridges stacked like coins, ran the full length of the top surface. 50 rounds. Traditional systems achieved that capacity with magazines hanging 30 centimeters below the grip. This design kept everything within the outer profile. Prédaza picked it up, brought it to his shoulder. The short length made it feel like a large handheld device with a stock. The weight balance is forward, he said. The magazine is essentially a tube of metal sitting on top of the mechanism. Better than hanging below, Denis replied. Vehicle crews are the target user. This fits between seats, under dashboards, in door pockets. The challenge wasn't just dimensional, it was systematic. The cartridge needed to defeat protective gear without generating heavy recoil in a lightweight package. The magazine needed high capacity without increasing length or width. The operating mechanism needed reliability despite the unconventional feeding geometry. And the entire system needed to be manufacturable at scale for NATO procurement. The geopolitical tension was ending, but its technical legacy remained. Armor technology had advanced to the point where 9mm rounds and even 45 ACP became ineffective beyond close range. Meanwhile, standard 5.56mm rifles were too long for the expanding population of support personnel who needed more than sidearms, but couldn't maneuver full-sized gear in confined spaces. Denis set the prototype down. "We test the feed mechanism tomorrow," he said. 50 rounds. Gravity-assisted, but not gravity-dependent. The rotation has to be consistent. The design embodied a specific bet, that velocity could replace mass, that horizontal could replace vertical, that synthetic materials could replace traditional steel and wood. Everything conventional had been questioned. What remained was the minimum required to solve the problem NATO had defined. If stories like this help you see how engineering quietly shaped history, tell us in the comments what surprised you so far. And stay with us for the next chapter. The NATO document had arrived at FN Herstal in 1986, distributed simultaneously to manufacturers across Europe and North America. The requirement was titled Personal Defense Weapon, and it outlined a new category that didn't yet exist. Too heavy for a pistol, too short for a rifle, more powerful than a submachine gun. The specification included minimum penetration standards against Chrysat armor, a titanium and Kevlar composite representing protective equipment at ranges where pistols were essentially useless. Denis knew that Heckler & Koch in Germany was working on their solution. Steyr in Austria had a team assigned to the problem. Colt in America was exploring options. The winner would potentially supply hundreds of thousands of units to NATO forces. The loser would have spent years of development funding on concepts that would never leave the prototype stage. The cartridge question came first. FN's ballistics team, led by Denis's longtime collaborator Mark Newforge, had been experimenting with scaled-down rifle rounds since 1986. The 5.7 to 28 mm emerged from systematic testing. Small enough to allow high capacity, fast enough to maintain energy at 150 meters, light enough to keep recoil manageable in a 2-kilogram unit. The cartridge determines everything downstream, Newforge explained during a design review in early 1989. Bolt weight, spring tension, chamber pressure, barrel length. We're operating in a narrow window where the physics work. The bottleneck design, wider at the case base, narrowing toward the projectile, mimicked rifle geometry at miniature scale. The projectile weighed just 2 grams, but traveled at velocities normally associated with intermediate rifles. Penetration came from speed and design rather than mass. Dennis faced the magazine challenge next. 50 rounds of 5.728mm ammunition stacked in a single feed column would create a magazine 35 centimeters long, longer than the entire unit was supposed to be. Double-stack magazines reduced length but increased width and complexity. Drum magazines added bulk and weight. The horizontal orientation appeared in his sketches in August 1989. Lay the cartridges flat, stack them in a double row, feed them downward through a rotating mechanism. The magazine would sit along the spine, adding minimal width, keeping the center of gravity between the hands. René Predazza, who had joined the project to solve the ergonomics, built a wooden mock-up to test the handling. "It's counterintuitive," he said, shouldering the carved block. "Users expect to see the magazine below, not on top. But in a vehicle interior, this makes sense. Nothing projects downward to catch on seat frames or door handles." The team worked in parallel on the bullpup configuration, action behind the trigger, to maximize barrel length within minimal overall dimensions. A 26-centimeter barrel could be fully enclosed in a unit measuring just over 50 centimeters total. By late 1989, the prototype existed. Polymer chassis, top-feeding magazine, ambidextrous controls, integrated optical sight rail. It looked unlike any equipment NATO forces had carried. That was either the solution or the fatal flaw. The magazine's internal mechanism was the technical heart of the entire design. Dennis and the engineering team faced a problem that sounded simple but defied obvious solutions. How to rotate cartridges 90 degrees while feeding them reliably downward from a horizontal stack. Inside the transparent polymer magazine body, 50 cartridges rested in 2 columns, oriented perpendicular to the bore axis. At rest, they lay flat, bases toward the rear, tips toward the front. When the bolt cycled, a spring-loaded follower pushed the stack forward, feeding cartridges one at a time into the spiral ramp mechanism. The ramp was a 3-dimensional helix machined into the magazine's base. As each cartridge entered, it engaged a curved track that guided it through a 90-degree rotation over approximately 4 centimeters of travel. The geometry was precise. Too shallow an angle and the cartridge would bind. Too steep and it would fail to rotate completely before reaching the chamber. A team member named Luc Verdun had spent months refining the ramp profile using progressive prototypes. Each iteration was tested with dummy rounds, cycled manually thousands of times to identify friction points and binding conditions. The cartridge base had to remain controlled throughout the rotation. No wobbling, no jamming, no variation between the first round and the 50th. "The spring tension is critical," Verdun explained during a technical review. "Too much pressure and the cartridges jam in the curve. Too little, and the feed becomes gravity-dependent, which means the equipment wouldn't function reliably in non-vertical positions." The final design used dual springs running the magazine's length, providing consistent pressure across the full 50-round capacity. As cartridges fed out, the follower maintained contact, ensuring the next round was always properly positioned for the spiral transition. The ejection system had to complement the top-feeding mechanism. Spent cases couldn't eject upward. The magazine occupied that space. They couldn't eject rearward. That's where the user's face was. The solution was forward-downward ejection with a port positioned ahead of the trigger guard. Cases tumbled out and down, clearing the unit regardless of the grip or stance. Dennis watched the first live-fire test in March 1990 at FN's proving ground outside Liège. The prototype sat in a mechanical rest, loaded magazine visible through the polymer housing. The test engineer activated the trigger remotely. The unit functioned, cycled, and functioned again. Brass cases arced forward and down, landing in a growing pile on the gravel. The distinctive sound, sharper than a pistol, flatter than a rifle, echoed off the concrete walls. 50 rounds cycled without interruption. The magazine was empty, the bolt locked open. No jams, no failures to feed, no extraction problems. The spiral mechanism had worked exactly as calculated. Predazza retrieved the equipment, released the empty magazine, examined it. "The follower is seated properly," he said. "No deformation, no binding marks on the ramp surface." They loaded another magazine and tested again and again. After 300 rounds, the mechanism showed normal wear patterns but no failures. The top-feeding rotary system, the element that made every other design choice possible, had proven itself under actual operational conditions. Do you think this design choice was inevitable or a risky gamble at the time? Share your view in the comments and pass this story to someone who enjoys understanding how things really work. The NATO requirement specified CRISAT armor penetration at 150 meters. CRISAT, an acronym for the test standard, consisted of titanium plates backed by Kevlar layers, representing protective equipment. The 7,028mm cartridge had been designed specifically to defeat this target, but design calculations and actual performance didn't always align. The test facility at FN's range included a ballistic tunnel with panels mounted at measured distances. Dennis and the ballistics team set up CRISAT targets at 150 meters, then at 100 meters for baseline comparison. The prototype P90 was secured in a mechanical rest to eliminate human variables. Mark Newforge handled the ammunition inspection, checking that each cartridge met specifications for powder charge, projectile weight, and case dimensions. The SS-190 ball round, the designation for the armor-piercing projectile, used a steel penetrator core wrapped in an aluminum jacket. At 715 meters per second, the small projectile carried enough kinetic energy to punch through protection that would stop conventional pistol rounds. The first shot at 150 meters produced a clean perforation through the CRISAT panel. The entry hole was precise, the back face showing complete penetration. They fired 9 more rounds at the same target. 10 for 10 penetrations. The velocity from the short barrel was sufficient. "Energy retention is better than modeled," Newforge noted, examining the target under magnification. "The bottleneck case design is efficient, minimal velocity loss over distance." They tested at 200 meters, beyond the specification, and saw reduced but still consistent penetration. At 50 meters, the projectile over-penetrated, exiting the back face with substantial residual velocity. The effective range envelope was wider than NATO had required. The recoil characteristics were measured next, using accelerometers attached to the prototype. Peak recoil impulse measured approximately 1/3 that of a 5.56mm NATO rifle, despite comparable muzzle velocity. The light projectile mass made the difference. A user could control the equipment in rapid succession without the barrel climbing off target. Accuracy testing revealed the limitation inherent in the design. The short barrel and compact dimensions limited precision at extended range. At 100 meters, groups measured approximately 20 centimeters, acceptable for a defensive tool but nowhere near rifle accuracy. The P90 wasn't meant to replace precision tools. It was meant to give vehicle crews and support personnel a fighting chance if confronted. Environmental testing followed. The prototype was exposed to sand, mud, water immersion, temperature extremes from -20 to +50 Celsius. The polymer construction showed advantages over traditional steel: no rust, no wood swelling, minimal thermal expansion. The magazine feed system proved surprisingly resistant to contamination. The enclosed, top-loading design kept debris out of the mechanism. One failure mode emerged during reliability testing. If the unit was dropped directly onto the magazine while loaded, the impact could occasionally dislodge cartridges enough to cause a feed interruption. The solution was a reinforced magazine locking mechanism and a redesigned follower with better retention geometry. By June 1990, the validation testing was complete. The P90 had functioned over 10,000 times across multiple prototypes without critical failures. Penetration met specifications, reliability exceeded requirements, and the dimensional constraints had been satisfied. The system worked as a coherent whole. FN submitted the final documentation to NATO in July 1990. The geopolitical landscape was shifting. Germany would reunify in October. But the technical problem the P90 solved remained relevant. Asymmetric challenges, vehicle-based operations, and the need to equip support personnel effectively weren't disappearing. If anything, post-tension environments would make those requirements more acute. During a NATO technical review in Brussels in September 1990, a panel of evaluators examined the P90 alongside competing designs. Heckler & Koch had submitted the MP7, also chambered in a high-velocity cartridge. Colt had developed a compact variant. Other manufacturers presented conventional solutions, shortened rifles or enhanced subunits. The evaluators handled each design, compared dimensions, reviewed test data. When they reached the P90, the top-mounted magazine drew immediate attention. One evaluator, a French logistics officer named Colonel Marchand, held the unit vertically, horizontally, and upside down. "This feeds in all orientations?" he asked Dennis, who was present to answer technical questions. "Yes," Dennis replied. "The spring tension is calibrated to maintain consistent feed pressure regardless of position. It's not gravity-dependent like traditional vertical magazines." Marchand set the unit flat on the table, magazine facing up. In a vehicle incident or confined space, traditional magazines can prevent the equipment from lying flat or create interference points. This eliminates that problem. The revelation wasn't just that the horizontal magazine was clever engineering, it was that the design choice enabled tactical flexibility that hadn't been explicitly required. A unit could be stored, carried, and operated in positions where conventional magazine orientations created mechanical conflicts. Dennis explained the dimensional logic. A 50-round vertical magazine extends approximately 30 centimeters below. In the vehicle interior, that projection catches on seats, door frames, and equipment mounting points. It prevents compact storage. The horizontal configuration keeps everything within the rectangular footprint. Another evaluator asked about magazine changes under stress. Dennis demonstrated, release the magazine catch, pull the empty magazine straight back off the spine, slide a fresh magazine forward until it locks. The motion was linear, not angular like traditional changes. In darkness, or while wearing gloves, the simplified geometry reduced fumbling. The optical sight mounting was another consequence of the horizontal magazine. With the magazine sitting on top, the sight rail ran directly along the center line at a lower height than conventional configurations. The sight picture remained consistent, and the optical axis stayed close to the bore axis, reducing parallax at close range. What became clear during the evaluation was that the horizontal magazine wasn't an isolated feature. It was the organizing principle that made every other design choice coherent. The bullpup layout worked because the magazine didn't interfere with the trigger group. The ambidextrous controls made sense because the feeding mechanism was symmetrical. The forward ejection was necessary because the magazine occupied the top surface. The compact length was possible because the magazine didn't add external dimensions. One of the ballistics engineers on the panel, a German named Klaus Reiter, summarized it during a break. "Most tools are mechanisms that happen to be packaged. This is a package that happens to contain a mechanism. The dimensional constraints drove everything. The P90 received NATO qualification in October 1990. Adoption would follow gradually. Belgium first, then other NATO members, then specialized units worldwide. But the technical validation was complete. The system functioned, the cartridge performed, and the horizontal magazine system had proven both functional and advantageous. Dennis kept one of the early prototypes. Years later, he would tell engineering students that the most important lesson from the P90 project wasn't about equipment. It was about questioning conventions when constraints changed. For a century, magazines had been vertical because that's where they fit on larger systems. Once the requirement changed to ultra-compact dimensions, vertical was no longer optimal. The horizontal solution was obvious in retrospect, but it required abandoning what everyone assumed was fundamental. By the late 1990s, the P90 had entered service with various units across 30 countries. Its adoption pattern revealed something unexpected. The equipment found its primary users not on conventional fields, but in specialized roles where dimensional constraints mattered most. Specialized teams appreciated the compact size for building entries. Security details valued the balance of capability and concealability. Vehicle crews finally had a tool that fit their workspace. The personal defense weapon category that NATO had defined in the 1980s never fully replaced pistols or rifles as the specifications had optimistically projected. Instead, the P90 created a niche that hadn't clearly existed before, a space between sidearms and primary equipment for situations where immediate defensive capability mattered more than sustained engagement or long-range precision. The 5-point FN 28-meter cartridge, developed alongside the P90, became available in other platforms. FN developed the 5.7 handheld chambered in the same round, offering compatibility for units that adopted the P90. The cartridge's armor penetration characteristics and low recoil made it valuable beyond the original application, though its effectiveness remained bounded by physics, superior to pistol rounds against armor, inferior to rifle rounds against targets beyond 200 meters. From an engineering perspective, the P90 demonstrated what became possible when dimensional constraints were treated as primary design drivers rather than secondary considerations. Jean-Paul Denis retired from FN Herstal in 2004, having worked on subsequent variants and refinements of the original design. In interviews, he emphasized that the success came from accepting what the NATO requirement actually meant. Not make a smaller rifle, but solve a different problem entirely. The horizontal magazine system influenced subsequent compact designs, though few manufacturers adopted the configuration directly. The patent specifics and manufacturing complexity created barriers to direct imitation. More importantly, the P90's top-feeding mechanism was optimized for a specific cartridge geometry and size. Scaling it to other dimensions introduced new challenges that often negated the advantages. The equipment's cultural visibility exceeded its tactical deployment. The distinctive profile, bulky where tools were expected to be slim, flat where they were expected to be vertical, made it visually recognizable. Entertainment media adopted it as a signifier of futuristic operations, which ironically made a 1990s design into a symbol of future technology and fiction produced decades later. But the engineering reality remained grounded in the specific problem solved in that FN Herstal design studio in 1990. 50 rounds of armor-defeating ammunition in a package shorter than a human forearm. The horizontal magazine made it possible. Everything else, the bullpup layout, the synthetic construction, the ambidextrous controls, the forward ejection, followed from that central geometric decision. René Prédazer, who had worked alongside Dennis on the ergonomics, noted in a 2010 technical retrospective, that the P90 succeeded because it abandoned assumptions about what such equipment should look like. "We designed it to work, not to resemble existing designs," he wrote. "The result looked strange because the requirements were different from what had come before." The FN P90 remains in production 35 years after its introduction. The basic design has seen refinements, improved optical mounting systems, modified stock configurations, accessory compatibility, but the core mechanism remains unchanged. The horizontal magazine still rotates cartridges through that helical ramp. The unit still measures just over 50 centimeters. The dimensional problem that drove its creation still exists wherever personnel need more capability than a pistol in less space than a rifle allows. If you enjoy calm, true stories about how engineering shaped the world, subscribe to the channel, leave a like, and tell us from which country you're watching.